Assalamualaikum warahmatullahi wabarakatuh and a very good day to our lecturer, Technologist Ezri bin Muhammad. Today our group 11 from section 8 is very proud to present our multivariable calculus. Project title is Volume Calculation of an Industrial Reactor with a Multi-Faceted Roof and Hollow Shaft. My name is Zanata Fitri binti Abu Sama and my metric number is DE240039 and I will be a kickstart to our presentation today. Before we dive deeper, let me introduce the dedicated engineer of Group 11. First, our leader is Sheikh Akmal Hakim bin Sheikh Anhak. Second is Sebastian Engau Stephen. Third is myself, Zainati Fitri binti Abu Sama. Fourth is Nur Shahinda Alia binti Hairul Anwar. And finally, our team members is Ainul Sakina binti Zulkifli. Together, we have successfully modeled and verified the fluid capacity of this specialized reactor structure. Now, let us look at the core of our project, which is the industrial reactor geometry. As you can see on the slide, imagine an engineering setup where fluid must be contained efficiently within a hemispherical autodome. The maximum boundary is limited by a radius of 5 units, sitting on completely flat floor at z equal to 0. However, the real design challenge begins inside. A vertical cylindrical cooling shaft with a radius of square root 2 units runs right through the center to control internal heat because this core tube is entirely sealed. It acts as a dead zone that cannot store any processed fluid. Capping the structure is a unique double slope roof that trims the top volume. Therefore, our exact thing to do is to calculate the precise space trapped between these geometric intersections. Now, to solve a complex three-dimensional problem like this on the slide, Cartesian coordinate will lead to highly tedious equation. Instead, our methodology leverage the power of triple integrals in cylindrical coordinates. Since our reactor structure share a common circular center at the origin, transforming the parameter using x equals to r cos theta and y equals to r sin theta completely simplify the boundary setup. As the outline in our subtraction scheme, our mathematically strategy follow a systematic reduction logic. We first integrate along the vertical height z bounded from the floor to the hemisphere shell. Then we set the radial limits r from the outer edge of the hollow shaft to the hemisphere wall, spinning the full domain from 0 to 2 pi. This allows us to find the base fluid capacity before subtracting the roof clearance. To show you how this beautiful integration is carried out step by step, I will now hand over the floor to our calculation and simulation expert. Thank you.
For this slide, we show the MATLAB coding that was used to verify our manual calculation. The code is divided into two main parts. The first part is the calculation part where we define the given values such as the radius of the hemisphere, which is r equal to 5, and the radius of the hollow shaft, which is square root 2. After that, MATLAB calculates the volume of the hemisphere, the volume of the hollow shaft, and the usable volume before considering the roof. Then, the volume of one roof cap is calculated and multiplied by 2 because there are two symmetrical roof caps. Finally, the final usable volume is calculated using V final equal V base minus 2 V cap. The second part of the coding is used to generate the 3D graph. In this part, we use MATLAB commands such as sphere, max grids, and surf to plot the hemisphere, hollow shaft, roof plates, and reactor floor. So this coding helps us check our manual calculation and also give a clearer visualization of the reactor structure.
This slide shows the result obtained from MATLAB. From the command window, MATLAB displays the calculated values step by step. The volume of the hemisphere is approximately 261.7994 cubic units. Then the value of the hollow shaft is subtracted giving the usable value before the roof as approximately 231.0204 cubic units. Next, the volume of one roof cap is approximately 4.2228 cubic units. Since there are two roof caps, the total roof volume removed is approximately 8.4457 cubic units. Therefore, the final usable volume obtained from MATLAB is approximately 222.5747 cubic units. This value is very close to our manual calculation, which is rounded to 222.58 cubic units. The 3D graph also shows the reactor model clearly. The blue part represents the outer hemisphere, the grey cylinder represents the hollow shaft, the orange and green planes represent the roof planes, and the yellow surface represents the floor. Overall, the MATLAB simulation supports our manual calculation and helps us visualize the shape of the reactor more clearly.
Hello, my name is Sebastian Ngau. My matric number is CE240231. So I will explain about the calculation. So first, looking at the geometry of our system, we have an inner cylinder with a radius. R is equal to S2. So an outer hemispherical dome with a radius of 5. Because the shape has circular symmetry, it is the best model using cylindrical coordinate. So this gives us our three integration boundary. So the first is the angle goes from 0 to 2 pi for a full rotation. So next is the radius r span from the inner wall at 2 and the outer edge at 5. So the third is the height z start at the reactor floor, which is z is equal to 0, and goes up to the hemispherical roof, which is z is equal to 25 minus r square. Next, we go to the integration using the volume element dv equal to r dz dr and d theta. I set up the triple integral. So the first is integrating with respect to z is straightforward and give us r 25 minus r square. Next is to evaluate the radial integral from 2 to 5. I applied u substitution by letting u is equal to 25 minus r square. And then after adjusting the limit of integration from r to u, the inner integration simplifies beautifully to a value of 1 per 3 multiplied to 23 power of 3 per 2.
Hi, Assalamualaikum. My name is Syah Mahakim bin Shana. My matrix number is CE240220. Now let's move on to the final integration phase of our volume calculation, where we integrating our previous result with respect to theta to find our baseline volume. Our integral setup is the integral from 0 to pi of 1 over 3 times 23 to the power of 3 over 2 d theta. Since our third, what, since 1 over 3 times 23 to the power of 3 over 2 is completely constant with respect to theta, we can pull it right out of the integral. This leaves us with very straightforward integration. 1 over 3 times 23 to the power of 3 over 2 times the integral from 0 to 2 pi d theta. Integrating the theta simply gives us theta evaluated from our limits of 0 to 2 pi. 1 over 3 times 23 to the power of 3 over 2 times theta evaluated from 0 to pi. Plugging in our upper limit of 2 pi and subtracting the lower limit of 0, the expression becomes 1 over 3 times 23 to the power of 3 over 2 times 2 pi. Rearranging these terms gives us our exact value, 2 pi over 3 times 23 to the power of 3 over 2. When we compute this decimal approximation, we get baseline volume of 231.02 cubic units. Next, we need to account for the caps. The volume of a single cap V cap is calculate using the formula V cap equals pi over 3 times 250 minus 100 and 10 square root of 5. Evaluating the expression gives us approximately 4.22 cubic units. To find our final total volume, we take our baseline volume of 231 points of zero point zero 0.02 and subtract the volume of two caps. Volume equals to 131.02 minus 2 times 4.22. This brings us to our final total volume of 222.58 cubic units.
Hi, it's me again, Zainati Fitri binti Abu Sama, and I will conclude our presentation today. Based on the detailed calculation and simulation presented by my teammates, our systematic geometric subtraction has successfully yielded precise quantitative result for each section of the reactor. As displayed on the slide, the raw hemispherical dome provide our baseline capacity at 261.80 cubic units. After excluding the 30.78 cubic units displaced by the central cooling core and further subtracting the 8.5 8.45 cubic units trimmed away by the twin slope roof plane. Our final net usable fluid capacity precisely at 222.57 cubic units. Most importantly, cross-verifying our manual hand integrations, again the computational engines of MATLAB yielded an exact 0% error margin, proving that our mathematical model is absolutely flawless. This project beautifully demonstrates how multivariable calculus serves as a critical, real-world tool of precision engineering design. That concludes our presentation from Group 11. Thank you very much for your time and attention.